level and the trends. So as we see from R&D and systems, basically. So what in the future? So I won't spend too much time on this because I know you've been doing this. You're part of the PhD school, so you know about KTH and our division. So, but I work in the division of heat and power, like Bjorn said, and there in this division we look into different areas of research. My area of research, so the 6 areas are here, and my area of research is kind of touching upon all of them, but mainly perhaps on centralized renewable energy systems where I focus the most. They're including solar. My background, Bjorn just briefly mentioned it as well. I'm an engineer myself. And then I did my PhD at KTH in solar energy with storage, and I lead different projects at KTH and advise different companies in the sector, renewable energies as well. And so for today, what I put here are, and by the way, you know, feel free to interrupt or ask questions as we go, since we have only 1 hour. So just put on mute and then directly ask. I think it's the easiest. I'll talk a little bit about you know, background to solar energy, since I don't know exactly where we are out there, and I think it's important so that you understand maybe definitely technology later, but the potential for solar energy, about solar resource assessment, and then moving to PV, where we're going to stay for the rest of the hour. So in terms of potential, and I guess this is something you're pretty much familiar to because you've been in the program this week already. The potential for solar energy is, when you look into renewables, is probably the largest. So, oh, we have a, okay. It's probably the largest among all renewables. And what you see here on this slide is just an indication of size in terms of potential comparatively. And the reason is, you know, some believe actually that wind and other technologies actually derive from solar energy. But maybe regardless of which one, you know, is the one that originates all these available renewable energy, what has been actually estimated is that the potential in terms of energy that radiates Earth, considering you know, comparatively to the energy that we need and the other energy renewable sources, is 3,000 times the energy that we need. So you see here that solar energy is 3,000 times the energy we consume, or our global demand, and that meaning electricity, heat, transportation together. And it's way larger than, let's say, the second most available renewable source, which is wind, which is 200 times the energy we need, and so on. So maybe the key message here is that, you know, if we were to move towards sustainable development and look into the SDGs, goal 7 is to ensure access to affordable, reliable, sustainable, and modern energy for all. If the basis for such were to be renewable energies, which I believe is a combination of different solutions, we see that solar energy certainly will play an important role because it's the most abundant one. Now, if we move into a little bit more into this potential, like Bjorn mentioned, the potential is not evenly distributed on Earth. So what you see here in this slide is basically those areas of the world in red, right, where the potential is highest. And should we, like I said, you know, decarbonize our grids to avoid well, the problems that come together with global warming, solar energy will play an important role, and particularly in those areas that are, you know, darkest red here. Now, the block that I, you know, put together here in the middle of the map, in a very dark area, it's a square that, in area, just to give you an idea, that area, that white block, would actually be sufficient to cover all our energy needs if we were to deploy in that area only technologies that we have today. So if, let's say, if we cover that area with PV or concentrating solar, that will be sufficient to cover our energy needs in terms of power produced. Now, of course, you may wonder, we cannot do that. First of all, this area is uninhabited at all. So there's nothing there that's the Sahara. But second is also that, you know, another big issue is where we consume it, which is different from where the power is produced, right? So we could actually certainly have that potential there in the middle of the Sahara, but, you know, the probably dense area are probably in Europe, Americas, you know, so then together with you know, this uneven distribution comes the challenge of that, okay, it is not distributed evenly, but also it's variable, as we'll see in the next slide. And secondly, you know, it's not really matching when we need it and where we need it. So that is part of the challenges with solar energy. Then if we go more specific, some basics I wanted to have is, what is the actual potential? So first of all, if we assume the sun to be, a spheric body and using just black body radiation theory, the actual potential, what we call the solar constant at the atmosphere, so assuming this is the distance from sun to Earth, atmosphere level, the potential can be calculated, and it says that at the level of the atmosphere, the actual power that we receive from the sun per meter square is what we call a solar constant, and that is roughly below 1,370 watts per meter square. So that gives you an idea. As an engineer, I think it's always useful to have this, maximum theoretical potential, because if at atmosphere this is the maximum we could achieve, whenever you are on site and reading any measurement about what is the actual radiation at the moment, it should never be higher than this. And I will get to explain that actually it should be way lower than this. One of the reasons why it is lower than this is because, okay, let's say the potential is roughly 1,400 watts per meter square at the atmosphere. But then, as you know, between the atmosphere level and the surface of the Earth, there are a number of particles, clouds, etc., that we see every day. And I mean, we experience it every day. Some days are cloudy, and therefore they're not as bright. And some days are, or sunny, let's say, and some days are actually very clear skies, and you have, you can see the sun directly. So those effects we call atmospheric effects. And the fact is that the more the clouds, let's say, part of this radiation that gets to atmosphere gets actually reflected or scattered even more. When we have not that many clouds, then maybe only part of it gets scattered, but we can get as much of it from directly to surface. I think my point with this slide, and just to give you background there, so we say we know a potential at the atmosphere, which is roughly 1,400 watt per meter square. But then we have different effects in the atmosphere, I mean, from the atmosphere layer to the surface of the Earth, where we actually can install systems that let us have less irradiation, less potential even. And what we have, or what is defined then, is that there are two key components in terms of radiation. One is the beam, which is maybe the direct light, like you see here, the direct arrow. So whenever you are on surface and you can see the sun directly to you, that we call that radiation that hits you, that is the beam radiation, or also called direct radiation. Then the other big component is the diffuse. And the diffuse, it's basically, if you look at this graph on the left, the one that comes from everywhere. So let's say, after being reflected from the clouds, this layer of the atmosphere will reflect part of it back to the surface. And there will be some kind of reflection happening between clouds and the atmosphere. Part of it will go back to surface where we are. So that energy that still hits the surface, but it's not coming directly from the sun, but rather from the indirect phenomena happening, optical phenomena happening in the atmosphere, we call it diffuse. And it's important to know because depending on the technology we are talking about for harnessing solar power, some can harness the beam and some can harness both, and some can only the diffuse. Another very important thing to have in mind when we talk about solar energy and the resource. So let's say that is about what I said before was about the potential and actual values you can reach on Earth, right? Now the other important thing is that this potential, let's say, varies depending on the season where we are, our location on Earth. So first thing to keep in mind is that, okay, the Earth is rotating on its own axis, but also elliptically around the sun. So the fact that the axis of rotation of the Earth is also slightly inclined means that certain times of this year, by the way, this full rotation is a full year, certain times of the year, our location feels, or is actually a bit closer to the sun. And because of the angle of that this inclination has with the actual elliptical movement, then we're also more exposed to light. So let's say in the summer or in the winter, you have experience, if you have been, especially those that are in Sweden or so, you have been experiencing like the very drastic changes. So when we are in summer, we feel like very long days, when we're in winter is the opposite. And this is linked to this phenomenon. So the elliptical movement of Earth around the sun, and also the fact that the axis of the Earth is not exactly perpendicular to the, let's say, the radius of this ellipse. And this is more or less what I was saying about it. If I talk about the actual angle of inclination, so the inclination of this axis compared to the potential, let's say vertical, normal to the elliptical movement, it's 23 degrees, and we call that the declination angle. The declination angle is very important because when we start calculating the potential of the sun, and I guess two things. When as an engineer, as a solar energy engineer, there are two things. One is to measure the actual potential in terms of watts that we're receiving at every, instantaneously. But the other thing is where the sun is. So to position the sun, I think one of the key or one of the first angles to keep in mind is the declination. So the declination is this for, let's say, it's 23.5, understanding that this is the difference between the inclination of our axis of rotation and the normal to the sun. But depending on where we are, as I said, right, if you remember this elliptical movement, let's say for a location like us in the northern hemisphere, this will be summer, and that's why this explains a little bit, the bright area explains why us in the northern part of the world have more sun this time of the year. And this will be winter, where we're basically more, if you look here, like Stockholm is closer to this line, right? We are basically always dark, regardless of our rotation. And that explains, moving around. Of course, if you are in the southern hemisphere, it's the opposite and so forth. Only knowing the declination, depending on the day of the year, we can tell also how long the day will be in terms of hours of sunlight. So that already gives you an idea. And this kind of exemplifies what I just said. So we have this, the Earth is not rotating just perpendicular to the sun. There is this axis which is not normal. And say in a summer day for one given location in the northern hemisphere, we will have, the elevation of the sun will feel higher. So you feel like the sun is maybe in some locations even right above you. And in a winter day, you feel it more like, it's not even, it's very far away. And the elevation of the sun is not even half of the one in the summer. So you see that throughout the day, this is the different elevations that we will experience. So we feel different elevations of sun. So where the sun is with regards to ourselves. And you see this is an example actual for a location in the Midwest of the US, but in a way that applies for every northern hemisphere location. How the elevation in the summer, in the 21st of June, let's say, we can go as high as 73 degrees, whereas in the same location in the winter, the highest elevation of the sun is only 26 degrees. So understanding all of this phenomenon, it's important because when we design solar systems, we need to be able to track the sun properly. So we need to measure the sun, like I said before, understand the power that we have, but also where is it? And that, where is it depends on which day of the year are we and what time of the day is it. And now if I look back again more into the actual potential, this is, the first image I showed to you was a bit just on schematics. This actually is data taken from, this is free data if you go to the World Bank Group SMAP website. So you can see the actual potential depending on the coordinates where you are on Earth. And the global horizontal corresponds to that, considering both the beam and the diffuse that I mentioned earlier. So the total full potential on the horizon or on a flat horizon surface. And you see that there are areas of the world that have way larger potential than others. So, and if we look into our case, at least, if we go to Sweden, the global horizontal irradiation or the energy that we get per year is slightly a third of that other countries like in Chile or in the Sahara receive. So of course it makes more sense to have solar systems in those where there's 3 times more energy being received than here in Sweden, which doesn't mean that it doesn't make sense. I'm just saying that those areas are more prominent for solar energy in general, or there would be more cost efficient. And now you can see the difference between the global and the direct. So the direct is, that, like I said, the one that is directly, or the beam, not considering the diffuse. And you see that same locations that have good global have good direct because the global is the sum of both. But the direct, can actually show that even, before the Sahara and Chile were evenly the same sort of, but you see that Chile will even be better from a direct point of view. Also, so the area of Southern Africa or Australia or so forth. In our case in Europe, particularly the areas in the southern part of Europe are of course better for solar technologies. And if I look specifically to us, and I guess here is more of a mixed crowd here. In Sweden, we have a very, like I said, comparatively to the world, the potential is a third of that in the best locations, but still we have a, an uneven distribution. And there are some areas in Sweden where you see that solar energy would make more sense, especially in the south of Sweden, like I have in this map. And where I am now in Stockholm, you see that solar energy is not that bad. It still has some technologies being deployed there that could operate well, be cost efficient at these levels of irradiance, and especially they may be even further south in the island, Öland and Gotland. But having said that, so understanding, a bit about the background of solar energy, that it's unevenly distributed, that it's a function of time, and that depending on also the atmospheric effects that will have an effect on the actual potential on the surface, then we can move into technologies. So this potential is harnessed mainly today in the world by two key technologies. So that is, I'm mainly referring to power, by the way, to electricity. And that is by means of concentrating solar, which is what you see on the left. And that is a technology where you are basically reflecting the sunlight by a structure that we call the collector, and that is a mirror structure. So there are mirrors here. You are reflecting it to a surface, which could be a single point or a line, etc., where you could imagine that concentrating all this light here will create a very hot temperature point, and that heat can be extracted, and the heat is useful for driving any other process, in this case, conventional turbine system or power plant. Now on the right is the one that we'll be talking about after this slide, and that is solar photovoltaic. And solar photovoltaic is by far the most abundant, deployed solar technology. You've seen it in rooftops, you've seen it in large-scale systems, etc. It's everywhere in the world. I mean, we have producer manufacturers in Europe, China, US, etc. And the way, or you can use it at so many different levels because it's modular, as we will get to talk about. Each module can be part of a system or an array, and that array can be designed in a way such to satisfy different demands at the residential, commercial, or even larger scales. My field is mainly at the larger centralized systems, but of course the theory is the same. So any question there, I can explain why either both. But before moving into large-scale systems, I also wanted to review a little bit of the background of solar PV. So I think that very, very fundamental to understand why do we get electricity from solar PV comes down first to understanding semiconductors. So what you see on the left is basically the structure of an atom, right? And I highlight this because basically, as you get further from the nucleus, you have your last band. It's let's say the last two bands are the valence band and the conduction band. The valence band is the one that when we go to the periodic table elements, you see, what's the valence of each element, right? And the conduction is where they actually linked with the other elements and other atoms. So basically, at the conduction, you have free movement, let's say, and that's where we transfer energy kinetically or heat or etc. This distance between the valence and the conduction band can be measured in electron volts and energy, and that is called the band gap. And the band gap is then the energy that is needed for any loose electron in the valence band to actually move to the conduction band. Now, understanding that all elements have this type of structure, what makes a difference is that there's a difference between, insulator elements or conducting elements or semiconductors. Now, what you see here in A, B, C is the structure of, it's the same as what we have on the left, but I just put it in some kind of, bars. So you have your nucleus, let's say here, or, the bands here, and the nucleus here, and the conduction on the further top. What you see here is that A would be the structure of a typical insulator, so element. So basically in an insulator, you have your valence band with some electrons, but then there is a very wide gap, in this case the band gap, right, between the valence and the conduction. The fact that this band gap is so large makes these materials or these elements perfectly suited for insulating because they are very bad at conducting heat or kinetically having any movement between these electrons from band to band. So this is why we use this type of structured materials for insulating. Now the opposite is B. So B will be any type of metal. So metals are those where this gap or the band gap is basically non-existent. It's very minimum, which means that upon any type of excitement, could be light or upcoming radiation force or so forth, any electron can be freely moving between the valence band and the conduction band. So in a material made of this element, basically the conduction is very high. What happens is that electrons are very eager to move. There's a lot of kinetic movement effects happening inside, and in that sense, that's the reason why when we have all these metallic structures are used for conducting heat or electricity inside cables, for instance, right? Because they are perfectly suited for actually transmitting, for this effect to happen, to electrons to move. Now C, it's what we call a semiconductor. So semiconductors, if you look at them, they have the same structure as what the insulator had, but instead of having this very wide band gap, they have a relatively measurable confined band gap. So it's a band gap, an amount of energy that we can measure, estimate, and also influence, basically. So semiconductors, maybe like what I want to say here is that, okay, the fact that these have this narrow band gap allows to define, or to control when one electron can move from the valence to the conduction band. And therefore, semiconductors are used for PV technologies and other systems. And I'll go to that and why. But basically, the fact or the reason is that they are different from these other two because we can control when electron is moving, when one electron is moving, and also in which direction we want it to happen. Because as you can see in the conductor elements, electrons will be moving, but we cannot control the fact that there is no band gap. They will be moving freely, and they will be moving back and forth. So in this type of elements is where we let's say stay, and this is the background for PV technology. So a PV system, where let's say it's based or PV cell is based on the junction of two semiconductors, and that we call the PN junction. One negatively doped and one positively doped. And I'll get to doping, but basically semiconductors then can be, as we can find them on Earth, like raw, and you have some examples here, like diamond is a semiconductor, silicium is the most abundant and used semiconductor, so sand, and germanium. And extrinsic semiconductors, which are, these raw elements, but that we dope with small impurities, and the doping, we do it on purpose just to guarantee a better, let's say, movement of electrons in the direction that we want it to happen. When we put together two of these semiconductors, one negatively doped, one positively doped, we guarantee that this is going to happen, or this movement is going to happen from one negatively doped semiconductor to one positively doped, guaranteeing therefore a current. And when we create this current, then we can create what we call the PV effect. That is the background. This is why we use semiconductors. This is more or less what I was saying in terms of the junction. So let's say if you look at the left, you see, at the very much left, the structure of a typical semiconductor as we found in raw silicon structure. So let's say a number of silicon atoms put together. One atom of, if we modify, if we dope, let's say one atom of a silicon material with phosphorus, then it will become an N-type semiconductor. And if we do the same, but take a material and one atom we modify and dope with boron, it will be a P-type semiconductor, a positive P-type. And what happens is that they are all, let's say, if you look at the material, right, all of these are atoms that are, neutrally balanced. So it's still, each atom in itself is neutrally balanced. But now we have one of these atoms, which is actually not silicon, one of these one is actually boron. They are in itself balanced. But the fact that this has boron and it has phosphorus, then there is then in this particular one that we dope, one electron that we know is free or eager to move. And this is the opposite. Boron has more one hole, let's say, in the balance. So this one is willing to receive an electron at the minimum impulse. So when we put together one structure like this with one structure like this, provided that there is some energy, this electron will try to find its place here, creating a current when moving into this direction. And that is what we call the p-n junction. And the p-n junction is all the basis for PV cells, or what we call the PV effect. Putting together two types of semiconductors, one negatively doped, one positively doped, and expose them to light. When exposed to light, for as long as they are connected to a load or voltage, they will generate a current, and they will generate it specifically in this direction, from N to P. Now, phosphorus and boron are not the only doping elements we could use. Here, what you have on the right is a bit of an example. Assuming silicon is the semiconductor we're using for creating our cell, you could dope them with different elements here shown in blue or red. So this is what I was more or less explaining, what I wanted to I think I needed to explain that before getting here. So this is the basis for PV. So this is a PV cell, what you see here on the left schematically. So a PV cell where you have your p-type semiconductor in blue, so the positively typed semiconductor, or positively doped semiconductor. And you have here your negatively doped semiconductor, but put together by means of a metallic structure to guarantee the structure of the junction, and that including the rebounds and including the back cell resistance. The metallic structures are also helpful for us to guarantee that we can connect a load. So remember, for as long as there is a load connected, and if this receives any type of energy, or in this case light incoming, the incoming energy from the photons that come from the light will be enough impulse for the electron that is in the N-type semiconductor to jump to the p-type, and by doing this, it will create a current like this. This current will only happen, of course, if this load is connected, because otherwise there is no current flow at all. And this is what is depicted on the right on a more typical electrical engineering type of diagram, where you have, for as long as there is a load, you will have if this p-n junction is exposed to light, and the light is sufficient for creating for covering the band gap, what I said before, so the energy needed for one electron to jump from the valence band to the conductive band, then basically this effect will happen. We will have current happening, from the N-type to the p-type, and current times load is power, so that is basis for PV. So solar energy to electricity by means of excitement of semiconductor materials that are positively and negatively doped. Now, from a system point of view, schematically, then this is PV, solar energy to electricity by means of this effect. And of course, once in electricity, any type of system can also be integrated batteries or energy storage systems. So this is ESS. The cells look more like this. So before I was just showing an example of how they looked in a schematically, but this, what you have on the left, is an actual cell. What you see on from the cell, so you see you can differentiate the three ribbons, which we use to connect and to build a structure to guarantee the current circulation, or the circulation of electrons. And then the color itself denotes a little bit about which semiconductor we're using, and I think I'll have a slide for that. But the color tells us a little bit of if we are using silicon and pure silicon or not, or so forth. Now, let us go to a little bit of the limitations that PV technology has. So understanding how PV systems create electricity, then I want to talk a little bit about how the light actually generates this jump of electrons. So first, I think we should keep in mind, if we focus on the left, if you look at the spectrum of light, that the full spectrum can be used for generating this, for providing energy for creating this jump and creating the current. The issue is, though, that depending on the semiconductor that we choose, only they will be selective in terms of which spectrum is useful for that semiconductor, which part of the light. And typically, you see that for silicon, for instance, you can have all three parts of the spectrum. But for silicon, the electron, the energy that you need for guaranteeing that the one electron jumps from valence to conductive band and to guarantee the circulation of electrons and creating a current is only 1.1 electron volts. And understanding that the integral of this curve, and this curve will be varying depending on the intensity of the sun, right? But they always have this shape, but it will vary depending on how intense the sun is. So this is watt per meter per nanometer. Only part of the area is what I need, really, to make one electron jump. The rest, probably I won't need it. So in a PV cell, and this is an example of a silicon-based cell, let's say this greenish area is the actual energy that I need, so 1.1 electron volts, for guaranteeing that one electron will jump and create a current in a PV effect. Meaning that among all the other energy and all the other light that we're actually getting and that is useful energy, part of it, a fraction of it, is actually useful for me. What happens instantaneously at the PV cell then is that this all remaining energy becomes heat. And that is the main loss or main source of loss in a PV cell. And it's optical. It's just referring to how useful instantaneously which part of the spectrum I need to guarantee the movement of electrons, and then the other will convert into heat. And the heat is actually because electrons that are trying to move, but they already got the energy that they needed. So they are moving internally between the existing elements, generating heat because of kinetic movement. So this explains also why PV cells get hot. So a typical PV cell, you could say that when the ambient temperature is 25 degrees, you can expect that if they are in operation, they will be producing energy, and their temperature will be around 45 or more, depending on which how much is this area unused, right? Now, other optical losses that we see in PV cells are more in relation to the reflection that happens because of the structure that we have in situ. So how do we build the cell? So one is that the cell needs to be protected. So let's say here we have the negatively doped semiconductor and the positively doped one, right? We need to enclose them. So we enclose them in a glass. The fact that we use the glass, of course, we want a glass material that allows light to pass through as much as possible, but there's no such thing as a perfect glass. So there is some reflection in that surface. At the same time, part of the light that goes through the p-n junction and that provides the energy, but still there is light not unused, can be reflected from the rear structure that puts the thing together. So the rear surface of the cell. So that is energy that is also wasted, let's say. And of course, energy that is, if there is a ribbon, a metallic ribbon that it's heating, it's also exposed to light, that actually shadows a little bit my PV cell. So that is also energy that we're losing per meter square. So all of these are common optical losses. Understanding that the one on the left imposes most of the limitations of the technology in terms of efficiency. And this gives us a little bit of theoretical limits then, only with the thing that I just said about the phenomenon that I mentioned about which part of the spectrum is useful at any instantaneous time. So depending on the material we're using, so Shockley and Pweitzer proposed that, investigated, that you could have a theoretical limit provided mainly from this thermalization effect that I mentioned before, which is that only part of the energy that you receive you're gonna get. So at certain air mass, which on certain concentrations, they decided to plot what is this theoretical limit for a number of materials. And materials are characterized depending on the band gap that they need, so the amount of energy that they need. So at different air mass or path of atmosphere to surface distances and different concentrations of light, this curve will be moving. But generally speaking, what you see is that if we take let's say a typical spring or fall curve for air mass and a concentration of 1, so just the sun to us, we see how different material, different elements, different semiconductors used for PV manufacturing have a theoretical limit in terms of how much energy of the spectrum that we are receiving is actually used for producing electricity, and how much is for the rest, for heat or converted into heat. And this is what they depicted, and we see that for silicon-based PV cells, which are the most common because of abundancy of the material, the theoretical limit at the normal, spectrum and irradiance conditions, it's roughly a little bit below 30%, it's 28%. And we see today already in the market technologies that are 22%, 24%. So they are reaching the theoretical limit only from this standpoint. There are other elements, well, actually compounds or cadmium telluride, for instance, which have a slightly higher potential limit, but they involve rare materials which could be toxic when dismantling the unit, like cadmium. So of course there is a trade-off here, but overall, this tells you already an idea that PV has a limitation, an intrinsic limitation, which is that out of the spectrum, only part of it we could use for actually converting, generating current, and the rest will become heat. The higher the concentration, the more we can get a little bit more of efficiency out of it, but still then higher temperatures can be reached. Another effect that happens that will be also detrimental for the efficiency of a system, a PV system, it's recombination. So, excited carriers can actually recombine, and they will recombine. So in reality, it's not only about electrons, but the recombination is an effect where an electron that it's moving to the conduction band goes back to the valence band, which is undesirable. It means that you start generating current, but the current itself flowing in contraflow. This could happen out of a number of reasons, but the main is that, or usually when this happens, is that you need to have a balanced, number of holes and number of electrons willing to move from a structure point of view. And the fact that they are in constant movement, it could be sometimes that is, well, let's put it in a simpler way, not easy for an electron to find their pair, their whole pair in the other, positively doped semiconductor. And so it is easier for it to go back, not generating any current. And this is kind of affecting, what happens. You need to have a balanced picture. When you don't, then they might just try to go back to where they were. Now, recombination, one thing to keep in mind is that this effect happens whenever we have voltage, whenever we have a load connected to it, regardless if we have light or not. So whenever we have a load connected to a PN junction, electrons from the N type will try to move to the positive type. And that is regardless whether we have light or not, they will try to move in the opposite direction. And this is why there is an effect called the current in the dark. So that means, like what I just said, whenever voltage is applied, electrons will move in counterflow of the desired, create a current in the opposite direction as that we want. So they will demand electricity from the load or power from the load by trying to move backwards. Now, under current illumination, what happens is that you have so much energy from the light that you kind of reverse that flow, and you're able to actually inject, power to this, well, the current will diverge. So then basically you can have a positive power or generate power, understanding that current is, or the power is current times voltage. Now, this, the more you do this, so the more light you apply, will actually create more of this, electrons will be too excited, basically, to put it this way. So the more light we have, or to a certain point, you're going to have a maximizing effect of this recombination, meaning that up to a certain point, you can keep injecting light, and you can still have a positive effect in terms of producing power. But up from there, you will see that recombination starts to become, up to a certain point, recombination becomes too high. And in that case, to a certain voltage, and in that case, then basically power is no longer generated. And this explains a little bit of this, what we call the PV IV curve, so the current voltage curve. So now, as you keep increasing the voltage, because you have a certain light or so on, so the more voltage, recombination maximizes. What you do though is that in the dark, well, this happens, you're actually demanding energy from whichever load you're connected to, which is why it's important to actually disconnect any PV system or so on when we're not exposed to any light. And up to certain voltage, it's okay, but after some voltage, then basically this effect of recombination goes to infinite. And that puts another limitations in terms of how much power can an actually PV cell provide, regardless of how much light we provide to it. Now, this phenomenon, this PV effect, and all the different effects that I've mentioned, limitations in terms of power because of recombination or because of the amount of light that we can actually harness or not, has been represented in what we call them, or this PV effect has been represented in a circuit, in a simplified circuit, where you have the current provided by the light, which we call the photocurrent, the current that is generated in the darkness, which acts like a diode, and two resistances that are given from in relation to so the series resistance represents the metal contacts and the rear structure, And the shunt resistance represents a little bit of how this direct saturation current will behave and recombination will happen. So this is how we model or how we understand and how we study PV cells, where photolight is actually depending on the available irradiance that we have at the moment. This allows me to then explain what is the IV curve and the performance of a PV cell. So in the IV curve, what we're plotting is the current as a function of the voltage. Now, every cell has a characteristic IV curve, meaning that for every voltage, we can identify what is the respective current at which the cell is operating. And like I said, the more you increase the voltage, at a certain point, the combination is so high that that's why you see this drastic or sharp drop in current. And this point, or the maximum voltage a system can be attained to, or a cell, it's we call it the open circuit voltage. So in an IV curve, I think it's very important to differentiate the maximum current at which the system can operate, which we call the short circuit current, and that is when voltage is 0, or the maximum voltage that the system can happen before the combination is too high and we start actually getting energy from or demanding energy from the system, which is the open circuit voltage. Now, if power is current times voltage, you can also plot the orange curve, which is just I times V. And you see that there is always a point in the IV curve at which the power is maximized. And that we call the maximum power point of operation. And from a utility scale point of view, it's desirable because the purpose of a utility scale power plant, of course, is to try to sell as much power or to generate as much energy as possible, to sell energy as possible, as much as possible. The more power we can get out of a single cell, the better in that sense, right? So that is what we call the MPP, which you're going to come later. It's very important from a system architecture point of view because we're always tracking how to get there for every cell, for every module in the system. Now, in terms of performance, if you understand that the power that one cell gives you can come from this characteristic curve, where does irradiance and temperature come to play? So the more we have, we're exposed to solar energy, what happens is that the short circuit current increases. Because if you remember correctly, the current, which here the current is just the difference between the photocurrent and the diode current, then the more we have, light, then the value of this photocurrent will increase, which means the current will increase. So that means that this curve moves up, and you see how, at different irradiance levels. So here you have 250 watt per meter square, and here you have 1000 watt per meter square. This curve is moving up, which means that the cell can give me more power because if you look this dashed line, this is how the MPP point is moving. So the maximum power point is moving. Now, irradiance has almost no effect on the voltage of open circuit voltage. So you see that's why, regardless of the irradiance, the maximum voltage at which a cell can operate is already given and not that much influence. On the other side, you have the other big effect of operational effect and performance when operating a PV system, and this is the temperature. Temperature has almost no effect on the current, but it does have an effect on the open circuit voltage, which means that it actually, increasing the temperature, which is what you have in this line, so red is the highest, will have a detrimental effect on where is my maximum power point. So you can, the power that one cell can give you is reduced. Of course, the effect of this, it's relatively lower than when you have a full maximum irradiance. So there is a trade-off because you can imagine that in a very big power plant, if we're getting closer to talk about it, like I said, one of the most or best areas is in the middle of the desert. And there you will have a lot of irradiance, but you will also have very high temperatures. But having high irradiances pays off for these effects. Now, I'm going to get more close to systems. So the first subsystem that you have, moving from a cell, so understanding how each cell produces electricity. The first thing I want you to know then is that one cell, it's relatively useless because the amount of power that they provide is still closer to watts level. So 12 watts, 10 watts, etc. Now, the amount of our applications require more than just 10 watts. This is why we have put cells together in parallel and in series to create modules. So modules are nothing else but just structures where you have a number of cells in parallel or series. And therefore, when we put cells in parallel or series, we're modifying the IV curve of that total structure. So the IV curve of a module, let's say that has two similar cells in series, will actually move like what I show here on the bottom. So let's say that will increase, the voltage at which the system can operate. And for two cells in parallel, that will actually double the current at which the system can operate, keeping the same open circuit voltage. You can imagine that it has, modules have several in parallel, several in series. A typical structure will have usually the first modules were having 36 cells in series. Then soon after, it became two series of 36 each, so 72 cells. And then thereon. The reason why 36 was the first number is because back then, for the silicon-based cells that we had, at those levels, you produce enough energy to charge out a small battery, like a small battery of the ones we use for different applications. So then that's why we have a first 3D models for 36 cells in series. Now, modules on their own are not sufficient in a system. So this comes to power. This is the first slide where we actually talk about power plants. And a power plant or a PV system actually is a combination, or putting different modules all in a system, both in series or parallel, connected to a number of other equipment to guarantee the performance of or the control of how we produce electricity and so forth. So what you see here on this slide is, okay, a photovoltaic array is a number of modules that are connected in series and in parallel. And to do that, we need to have then a number of control structures where we call combiner boxes, for instance. And furthermore, one thing I actually haven't mentioned so far that's very important is that the electricity that comes from a PN junction, from a PV cell, is direct current. Most of our applications are actually alternate current. So in an integrated system, we need an inverter. In this case, a solar inverter that actually allows us to convert from DC to AC. Now, after the AC, of course, different steps can still happen. So you have different step-ups transformation processes to bring the voltage to the levels required by the grid. You have different, we call connection point requirements. And you might as well have batteries. Batteries could be both at the DC level or AC level. It's strategically depending on how the system. Another thing that is very important from a power plant point of view and array design is that, modules need to have tracking, and this comes back to or should have tracking when possible, or at least some kind of structure to maximize the amount of energy that they get. And this comes back to the beginning of this lecture, which is that, the sun is in constant movement. So we need to try to get as much as we can from it, when possible, follow it. A power plant will be then many of these arrays together. So let's say the size of this array, how much modules we can put together, is limited by how much, let's say, voltage and current this inverter can handle. But if we need more power, then what we will do is that in a power plant, we will just duplicate or triplicate or multiply this number of arrays, similar arrays, in a big plant. And this is what is shown here, more or less. So you can have a similar array on the left and on the right, each of them with their respective inverters. Each inverter connected to a step-up transformer from low to medium voltage. And then finally, a very big step-up transformer that goes from medium to high voltage so that we can connect it to the grid. Now, in a power plant, it's not only what happens there. Most of these things are actually happening, without any human interaction. But where we do come in place as human is, in the actual operational phase and seeing that the whole plant is performing as it should. Which can happen, like you say, in this 0.5 from anywhere in the world, basically. Now, this is how an actual plant will look like in real life. So what you see here in this slide, you see that this is a GIF of a plant in the middle of the desert. So you see how modules are all placed here in this type in kind of a string. A number of modules are placed together and basically tracking the sun. Choosing which tracking mechanism will depend on a number of reasons, but mainly economical. So there's always a trade-off of, okay, if you look at the right, how much more energy, which is what I'm depicting here, or how much irradiance can I actually get compared to not doing anything? So if I have a fixed structure, or if I have a structure that allows me to follow the sun, I'm gaining some area. So the trade-off between the energy that you're gaining or that you're able to collect compared to not having will actually, compared to the cost of it, will define whether you should go for a fixed structure like the one on the left, a single axis structure. So that means that you're following the sun in one axis like this. You see that they're only moving on one axis, or in dual axis systems like this, where you're following the sun continuously. So you're tracking basically always the direct normal irradiance. So I have only 10 more minutes, but I wanted to talk then for understanding a bit about the technology, what are the prospects. So I think it's very much familiar to all of you that the perspectives are globally that solar energy, understanding the potential it has and the need we have to decarbonize our grid will only increase. This is just an example from one of the main sources. This is from Bloomberg, but you see how as of today, 2021, the share of solar energy is not that much compared to our actual power coming from fossil fuels in the world. But in some years from now, should the plans from each country materialize, solar power will be undoubtedly the technology that is going to actually dominate the, let's say, energy provision in the world. And here you have in solar power both utility scale, which will be the most dominant one, but also small scale and systems. In terms of cost, and one of the reasons why solar power will be there is that, as you see here, these are the cost of the most prominent renewables we are today exploring. You have solar photovoltaic, concentrating solar, offshore wind, and wind in the last decade, and how they have changed. And you see how the steep decline for solar photovoltaic has been dramatic, and how they compare to this gray area, which is the fossil fuel cost today globally. So the cost per energy of solar photovoltaic in some locations is even way lower than this value here. So way lower than 30 or 40 megawatt per kilowatt hour, $40 per kilowatt hour, megawatt hour, sorry. But this is also happening in other technologies. So CSP is less deployed. I'm not talking about CSP today, but they are also reducing costs. And wind is almost also there. The cost decline is not as big as we've seen for PV, but it's also there. But PV, I mean, the expectations are that this will only continue, even though it's already very low. And the reason, or the driving force for this is chip manufacturing of all the modules and understanding how to do that better. If we look into Europe, I think maybe what you can look into the right is how it is expected that PV will grow dramatically as well. So we have in Europe some, existing PV installations. PV is not our major energy contributor, but it will grow dramatically should we meet our expected targets, and especially utility scale PV, which means that especially those in the southern parts of Europe, we're going to have a lot of PV power plants like the ones I showed earlier. If we look at another study from this is about how things are going to change from 5 years ago to 30 years from now. In the terms of solar energy, I mean, it's clear that most consultancies believe that utility scale will be the most dominant, let's say, system solution, even though maybe in Europe today, the share of residential, it's almost even with utility scale. Before finishing, I want to talk about future. So where are we? What do we do in research? There are different R&D perspectives for PV. So what you have on the right is a bit of a summary where we are today. Costs are decreasing in terms of install costs, levelized costs, and the capacity factor, which is the how much energy they actually produce compared to their from nameplate, it's increasing in average. Which means that we are making systems more efficient and also cheaper. There are different paths following that the scientific community is following to continue doing this. One is today most of the PV systems are silicon-based, either mono or polycrystalline. And operating at 20%. There is the belief that moving to other materials, to creating other junctions will increase its efficiency, for instance. So one high perspective happening now, and Europe is very active in it, it's having two junctions instead of a single one. So we call it a heterojunction. So a multi-junction where we can actually have two different semiconductors, and therefore being able to harvest different parts of the light spectrum, and therefore being able to reach slightly higher efficiencies. Another, and you can follow, by the way, this efficiency map at NREL. This is a free database where you can see the records for efficiency depending on which technology. You see blue is silicon-based cells, and the purple one, where the future should be, maybe it's for commercial systems, is still only in the lab, but it's for those systems that have more than one junction. With heterojunctions coming first to market, I believe, of course, only 2 junctions, and those having efficiencies closer to 30% theoretically. But you see other materials, other semiconductors stepping up and reaching commercial values of efficiency as well. Another very common trend, I think, in utility scale especially, there's no new power plant where we don't install bifacial PV, meaning PV modules both on the front and on the rear able to capture light. And the reason is that if you have a ground with very high reflective paint, for instance, high albedo, you can reflect a lot of the light that comes from the diffuse side and still harvest a lot. And PV itself, the junction, the manufacturing of the junction has become so cheap that it pays off to have a module facing downwards to the ground and harvesting part of this light, while at the same time, making use of the structure that I'm investing in to keeping the module here. You see bifacial PVs, different for fences, for, in the snow, of course, because snow is very high reflective, etc. Another big trend for PV in the future that we're looking into is, of course, the use from a system point of view, using PV to generate power that can actually be used to drive electrolyzers to produce hydrogen. So that is another path of research from a system point of view, on how to make better use of this integration from a control point of view, whether with storage or not, etc. We see a lot of PV now also happening in integration in buildings. Buildings, particularly in Europe, are responsible for 40% of our energy. So the more we can integrate PV in them and do it in a strategic way without damaging what we say, like the view of the building or the actual expected performance of the building, then we can get a lot of energy out of it. Another trend, it's floating PV. So from a system point of view, and that means that putting PV on lakes or calm water, and there are a number of benefits I'm highlighted here that these researchers claim. One clear one being that being close to the water allows to actually cool down the cells, which are being heated up by this kinetic effect that I mentioned, having more light than what we actually need for creating the current. Among others, they also claim that are good for the actual ecosystem there. And it's the same that for those researchers into agrivoltaicism, where we can have PV on crops, and the crops could actually benefit from the shadowing, and the water management could be better from a holistic point of view for such an integrated system. Okay, so I think that's mainly what I wanted to talk about today. So go from a bit of basics to what is happening in R&D today overall. So I hope it was at least entertaining.
Rafael, thanks very much. Very nice overview presentation of all the new developments, technologies, and